Yes, I find it puzzling because when I was young, I was interested in logarithms and powers of 2, but I really didn't like math. I hated doing addition exercises, anything repetitious, so I didn't like math in school. Until we started doing geometry, which I really enjoyed, partly because it was continuous progress. You could do it at your own pace, partly because there were no equations. But I think what really sparked my imagination in mathematics was not so much math itself as computers. And I grew up in a small town in Vermont, 2,000 people. And in 6th grade, I found a book in my father's closet, which was a guide to Fortran 4 programming language. And so I learned there was such a thing as a computer program, and I really wanted to try this. And they had a computer at the university in Vermont and a teletype in the high school, which was 10 miles away. And so I went and programmed on the teletype, which would print 10 characters per second. And I programmed the game of life and a few other things. I found that really exciting. I liked the immediate feedback. And in mathematics, there's a lot of logic and reasoning, but if you make a mistake in a proof, it's very hard to know. But if you make a mistake in a computer program, it doesn't work at all. So I really enjoyed having this sort of ratification of what I was working on. So I became interested in computers, I would say, more than math. Then when I went to college, I was open to many different disciplines. I went to a small liberal arts college, Williams College in Western Massachusetts, and studied psychology and philosophy and American literature and cinema, and but also physics and math. And what I really liked about math was that I could sometimes do the homework during the class, and then I had more free time. So I think what I really valued was, I enjoyed math, but I also really enjoyed having unstructured free time. And it gave me this. So then when I graduated from college, I didn't really know what I wanted to do. So I went to Cambridge, England for a year on a scholarship, and I took math courses there, and I discovered I really didn't like the way they taught college in England. And I had one application with me, which was to Harvard University for graduate school, and I sent this off, and I barely got in. So then I went, and I was suddenly surrounded by people who were real mathematicians, and I hadn't really had much education in mathematics, and it was very exciting and very intimidating at the same time. And I thought I might very well have a career in some other field. I would probably complete my Ph.D. in math, but who knows what would happen after that. And then I got to know some more about the world of mathematics. And I have to say that France and the IHES and the French Alps and my image of mathematicians in France played a big part in reshaping how I thought about mathematics as a career and how I thought about mathematicians as people. And I sort of heard some very romantic stories about mathematicians sitting silently around a fire in a small cabin in the Alps, and about what the IHES in Buhr was like. And so this began to change my interest in mathematics, or my vision of what it was to be a mathematician. That it wasn't all about problem solving and winning the Putnam exam or the Olympiad. And by the way, I wasn't very good at those problem solving contests. So in some sense, I was missing part of what is expected of a research mathematician. But the thing that I was good at, my teachers would say, was asking the right questions. And I now understand that in research this can be as important as having the technical power to answer the questions. Luckily that helped benefit me eventually in my career. But I would say the next thing that happened was I began becoming very interested in a connection between computers and mathematics, which had to do with some beautiful pictures of fractals that David Mumford was drawing at Harvard, and I became his computer programmer. And I really enjoyed the graphics and the visual artistic patterns that would emerge. And I enjoyed the computer programming, and I enjoyed starting to learn the mathematics behind it. And but then it turned out that David Mumford, who's really an algebraic geometer, didn't consider this as a field in which he could be an advisor for me. And Harvard is pretty small, so there were only a small number of fields in which one could work if you wanted to really work within the discipline of your advisor. But I was a little headstrong, and I got a hold of some lecture notes that Dennis Sullivan had written. And he was at that time a professor at the IHS. And I started a small seminar, and I lectured on these notes and learned a lot about what was going on in complex dynamics, which I found to be a great subject. I really liked it because one of my favorite subjects in math was one complex variable, and it's in a way very elementary and very geometric, and yet some really magical things happen and emerge there. And so then I was entering my 4th year of graduate school, and I had no thesis advisor, and I had no thesis. And the chairman, David Mumford, sort of took pity on me and called Dennis Sullivan in New York and said, would you talk to this graduate student of ours? He seems interested in what you're working on. So I flew down to New York City and met Dennis. And after meeting him a couple of times, I said, well, would you be my thesis advisor? And since he was a professor at the IHS, he had no graduate students, basically. Maybe he had one when he was at Princeton. So he asked what that would involve, and I said nothing. And then he sort of thought for a moment. He said, well, you better come with me to France this fall then. And so I went to the IGS for the fall semester, and I met Steve Smale at lunch at the IGS the first week I was there, and he gave me a problem which became my thesis problem. And I worked on it very hard through a whole rainy fall in Bure, and then that became my thesis, and it was very exciting. And so I went from having no advisor to having a good result. And so when I was about to graduate, I had several possible career paths, including one maybe working more with computers. I had been working in the summers at IBM's Research Center. But I realized that it was very hard to move back into mathematics if you left. So I thought I would give it a chance, and now here I am. Yes, this is pretty hard. So I like learning new things, and I like answering or working on questions that are, to me, seem obvious, but that maybe haven't been addressed even by the experts in the field. So I often am stumbling into fields where I'm not an expert and trying to do something which maybe people consider well-known or something like this. But so my research directions are originally I worked in complex dynamics, so the dynamical systems over the complex numbers with these beautiful Julia sets and so on. And Dennis Sullivan was probably the leading mathematician in that area, as well as Duody and Hubbard, who I met here in France at the time. And then but I also, after graduating, I went to Princeton University, where Thurston was at one of the most active stages of his career, and I learned a fantastic amount from being around him and the community that he had formed. So that was three-dimensional hyperbolic geometry. that was became another element of my mathematical world. And there's a beautiful idea of Sullivan's called Sullivan's dictionary, which says here's this discipline of dynamics, here's this discipline of geometry, and actually you can sort of go back and forth between these two. And and he had just proved a very deep result called the no wandering domains theorem by taking a famous result in the theory of Kleinian groups and more or less just translating it using this dictionary. And I found that mode of doing mathematics fantastic. His ability to capture a field in a broad and visionary way really inspired me. So anyway, those became my main fields, and I think that's still the area I feel most comfortable: complex dynamics, Riemann surfaces, Teichmüller theory, quasi-conformal maps. But I eventually ended up at Harvard, and those fields are not very well represented there. And one of my best friends, among my colleagues at Harvard, was Dick Gross, who's a number theorist or representation theorist. So I started to learn in a kind of amateurish way how to do some number theory, how to do some algebraic geometry, and I'm a little bit like a dilettante. I'm like somebody who has taught themselves how to play the guitar, so they don't actually know how to do it right, but I'm a dilettante in many different subjects. And so what I'm working on now involves all sorts of different things: K3 surfaces, Salem numbers, low-dimensional topology, so it's a broad field, and it doesn't have a name. But to me and to many of the other people working in the field, it's very clear that it's a single subject. Well, this is interesting because I wasn't on the Fields Medal Committee. So I have to say I don't really know, but I can tell you what I had personally considered the work that I was very happy with up to that time. So I think there were two areas where I had established some good results. One was on the classical problem of solving polynomial equations, like the quadratic formula. So this was something Smale got me started on. The question was whether you can solve polynomials by iterating rational maps that depend in some simple way on the equation you're trying to solve, and the answer turned out to be no for degree 4 or more, and yes for degree 3. There was a new algorithm that people had not discovered. So I found a new way of solving cubic polynomials, and I proved that you couldn't solve 4th degree polynomials. And it sounded very strange because what people know classically in mathematics is you can't solve 5th degree polynomials. So why can't you solve 4th degree polynomials? And it was because of the very strict rules Smale had imposed on what you're allowed to do. So with Peter Doyle, we weakened those rules, and then we discovered we could solve 5th degree polynomials. And so that was one of the most exciting research programs that I had carried through when I was young. And the solution involved a beautiful fractal object with the symmetries of the dodecahedron. And so I think I've always been attracted to low-dimensional, concrete, but perhaps canonical mathematical objects. And it was amazing to sort of discover a new one and draw a picture of it on the computer of something no one had ever seen before. It was like finding a new planet, or maybe a planetoid beyond Pluto. So that was one thing, but I think maybe the more significant thing was there was something called Krauss theta conjecture, which is a problem, very classical problem in complex analysis, but it could be viewed as a linchpin to prove a very deep result of Bill Thurston's, in fact, the one for which he got the Fields Medal, I would say, this geometrization conjecture, which was recently revisited by Perlman and resulted in the proof of the Poincare conjecture in the end. Anyway, Thurston had a very geometric approach to this problem, and very few people were able to absorb all of the mathematics necessary to understand it. And by studying this analysis problem, I was able to give a new analytic proof of the hardest step in that theory. So I think that those two things were probably what this award was for. But I have to say that, so Lippmann Bears, who was one of my mentors, also a complex analyst, used to say, mathematics is something we do for the begrudging admiration of a few close friends. And I never expected to get more out of it than that, and I think mathematics is plenty rewarding without any bigger recognitions, and I felt very lucky to have even been considered for the Fields Medal. I think there are many other people who would have been great candidates those years. Okay, so eureka moments. Okay, let me try to interpret your question. So it's definitely true that when you're immersed in a certain kind of mathematical problem that you are really struggling with some sort of central difficulty, and you get to know the problem inside out, and this difficulty becomes sort of something you face personally and can carry around with you, look at from a different aspect every day. And then if you're very lucky at some moment, you just understand how to get through it. And so I remember very well, it was probably my first moment of this type. So actually this I can draw at the blackboard, but maybe I should not now because, so when I met Hironaka, who was a professor at Harvard when I was a graduate student, he told me a problem about computing the dimension of a certain fractal shape based on drawing the letter M and then drawing it again inside of itself over and over. And interestingly enough, he had discussed this problem in a popular book for the Japanese public. And he had studied the problem himself. He wrote about it in this popular book, but he didn't know the answer. And so I thought, wow, this can be a problem for me to work on. And when you're a young graduate student, it's not clear what is worth pursuing that will make a difference to other people. So I started working on this problem. And I really knew it inside out at some moment. And it was becoming almost impossible to write down exactly my understanding of it. There were very complicated formulas. There were a lot of different mechanisms going on. But I remember walking home from the graduate school about 8 o'clock at night. It was dark out. I was crossing a street in Cambridge. And I remember very clearly when I got to the other side of the street, I knew the answer to this problem. And so that was in my experience, real insights often happen when I'm walking around. They almost never happen by sitting down at a desk and doing a calculation. In fact, I think I need some kind of stimulation, whether it's by working in a cafe or by moving around or something, talking to other people, to be able to really move forward on an argument. If I already know what I want to say, I can write down and work on it, but being inventive or creative is not something that comes easily to me sitting down. So that's one example of, that was maybe my first example of a real eureka moment. I think CIRM is great, and I think in general, I have a very positive feeling about mathematics in France. As I said, my thesis advisor, although he's from Texas, was a professor at the IHES, and there's also many other fantastic mathematicians in France. When there was a conference in honor of Perelman's solution of the Poincare conjecture, it was at the Institut Henri Poincaré, and there was a dinner with the mayor of Paris, and this would never happen in the United States. The mayor said there are more streets named after mathematicians in Paris than in any other city in the world. So I think there is a real appreciation of mathematics which CIRM represents, as a part of culture. And by a part of culture, I mean something akin to music, to art, as well as to science. It's not that it's not scientific, but it's that it's the intellectual side of the process, I think, is valued and respected here in a way that you don't feel all the time when you're a university professor and you're teaching undergraduates, perhaps, who don't want to learn calculus. So I feel there's a lot of joy in coming to a place where mathematics is considered as a special discipline. Mathematicians are considered special, and of course it's just, it's very super relaxing to have to not think about anything. So that your meals are there, the Calanque is there for recreation, the lectures are happening, and people that you might want to talk to all the time are suddenly all around you for a week. So yeah, I think CIRM is great, and I visited here many, many times, and I'm enjoying this visit as well.